right, so what operations do we have? We have a dictionary is a data structure. So when I say dictionary, think of a black box. We'll think about what to put inside the black box in a couple of slides. But let's look at what the knobs are on this black box. What operations do we want a dictionary black box to have? So we want to be able to search for things. And always try to remind yourself a dictionary is on pairs. It's a key value pairs. A dictionary data structure, you build the items have a key and a value, and the key are ordered. So the key have some logical ordering to themselves, and each key corresponds to some value. So when I say look in dictionary on set S for a key K, I'm not giving you the value, I'm giving you the key. I'm saying this is the key, what value does it correspond to? So in a normal dictionary, that would be, say, a word. And the word is the key, and what I'm asking you to return is the meaning of the word. So that's why it's in red. It's important that you remember that this is a key, and what I expect you to return when I give you this key is the element or the address to the element which it corresponds to. So in case of a normal dictionary, that would be the meaning. When I'm inserting, however, I'm giving you the element that I want you to insert. I'm giving you X, which is, I'm not giving you the key. So in this case, I'm giving you the element X, and you are supposed to insert it in the dictionary S. I'm not giving you the key. So this distinction is important, and that will change sort of why it matters is because that is what would affect the running time. What happens if I don't tell you the key? What is the first step you do? When I give you an element, you would have to find the key, and then you insert it at that place. So delete. So when you're deleting, again, I'm giving you the element, I'm not giving you the key, and you have to insert it in the set S. And whether or not we have to look for where to insert depends on how you're implementing these operations. So right now, we're just looking at what we provide as part of the parameter when we're running these operations. So you should be able to do search. You should be able to put things in the dictionary. You should be able to delete things from it. And then you should be able to return whatever the minimum element in the set is. And you should be able to give me, if I ask you what the maximum element in the set is, that is stored in the dictionary. And then you should be able to tell me the logical predecessor and successor. And why am I saying logical? Because it's not the order in which they're stored. It's not the physical ordering. It's the logical ordering that exists on the keys. So for example, the logical successor to, who was the president before Clinton? Before Obama, who was the president? Bush. All right. So logical successor of Bush is Obama. Is that right? All right. So Steve, if you look at his online lecture, he talks about President of the United States throughout the lecture. So I'm not very good at it, so I should come up with something else. But for now, like what you have to understand is that it may be stored in the dictionary itself in a different order. But when I ask you to give me a successor and predecessor, I'm asking you do it in the order in which the keys are ordered. So what is the logical successor of an element? In a dictionary, it would be the next word in alphabetical order would be a successor. It could be stored in an unsorted way. That's how you implement it. That depends on how you implement it. So it is the logical predecessor and successor. And now, there are tons of ways to implement these operations. They have different trade-offs depending on how you implement it. And so the problem of the day was on sort of let's look at one kind of way to implement these operations. And we're going to look at linked lists. So the problem was give the running time for all the operations if this is how you chose to implement what's in the dictionary. So you could use a singly linked list, and it's unsorted, or you could use a singly linked list, but it's sorted, or you could do doubly linked list sorted, doubly linked list unsorted. So as we'll see, this will change how fast the different operations are and their interdependencies. So when we analyze, we're going to look at, we can make something really fast at the cost of some other operation. And each of these ways to do it would be, the running time would be different. So let's start to fill up this table and go through why, what the running times are and why they're different. So suppose I have, let's start with unsorted. Suppose I have an unsorted singly linked list. So I don't have back pointers. I have my linked list, and it's sorted in the order of the keys, which is what the order is on. So now suppose I have to search in this linked list. I give you a key, and I say, what's the value? Look for this key and tell me what the value stored at that location is. So what would be the fast sort of running time, or what would be the running time that you can come up with? ON? Yes. So why is it linear? So because you would have to go every node starting from the head and be like, oh, is this the key that corresponds to this element? Is this the key that corresponds to this element? And you go through, in the worst case, you go through the entire list. It's unsorted, it's linked, so you can't jump around. So in the worst case, you're doing basically looking at everything and comparing at each step. So that's order n. So that's easy. Now, just so, I mean, we could fill it the way we want, but this, just so, what is it if it's sorted? What if the linked list is sorted in the, in the order of the keys? Yes. Yes, exactly. Excellent. Thank you. So it should be the same, but why it's still a sorted, yeah.
Because it's a linked list, so we can't use like a binary search algorithm.
Yes. Thank you. So, I mean, it seems like a sorted thing should be excellent for searches, but it's a linked list, so you can't jump around, so you can't binary search, because you don't have that option. You have to go sort of linearly follow the pointers. So even though it's sorted, we're not gaining anything from it. We still have to, worst case, I'll ask you, okay, search for the element that's the end of the linked list. So you go through everything, and then you reach the end, and you get order n time. So it doesn't really help for search if you have a sorted linked list. What about a doubly unsorted? So you have back pointers, and it's unsorted. I ask you to search for a key. ON? Yes, doesn't help. The pointers are not the problem. Like, you still have to go element by element and look through the entire list. And I guess it shouldn't be surprising that even though the linked list is sorted and has back pointers, if you're searching for a key, you still have to look at everything. Any questions why a sorted, doubly linked list would have a linear search cost? Even though it's sorted, even though you have back pointers, you still have to go through the entire list because your element could be anywhere, and you have to look for the value. Like, you have to go to the right place, retrieve the value at that place, and you might have to traverse the entire list. Yes?
The doubly sorted list, do you only have a pointer at the beginning, or do you have a pointer at the beginning and at the end too?
So doubly linked list, you have your, and in each step you have 2 pointers. And now are you asking whether there's a pointer here? No, just.
You have a pointer at the very first cell.
Mm-hmm.
You could also have a pointer at the very last cell.
Pointing to
that cell.
to itself.
That's not pointing to itself. Giving you the address of
Of the last item.
So you have an address for the header of the cell?
Yes.
You could have an address for the...
Okay, oh, I see what you're saying. So you want to keep a pointer to the tail. That's fine. So we know how to access the head. Suppose I know how to access the tail somehow. I just store it permanently, and I keep updating it. How is that half of OMN? Okay, I see what. So you're saying that, okay, suppose I kept a pointer to the head and the tail. It's just 2 pieces of information that I'm maintaining throughout. If the tail changes, I will update. You have to maintain this. You'll update the pointer every time the head and the tail change. And now you're saying, because it's sorted, I know whether my element is in the first half or the second half. Does that change the running time in order notation? No. It does make it faster by a half, but we don't care about sort of halves and twos right now. So we're just looking at the order notation, so it would still be order n. It could be half of what it was before, but yes.
Does it even necessarily make it half? Because you could have this list where you have, like, you're searching for 100s, and you start at 1, but then, like, your rest are, like, 100, 101, and then keep going up. So even if you have, like, the max and the
Even if you have the pointer to the max and minimum.
side, you start it when you go inwards.
You're right. Okay, you're right. So it may not even make it half because you don't know what the middle element is. The only way it could make it cut it in half is if I knew what was in this. So when you do binary search, you look at what sort of is in the center, and then you either go left or right, and that's how you cut the array in half. And here we don't know what it's in the center, so that's a very good point, that even though I do know what's in what's the minimum and the maximum, the distribution could be really skewed. So even though the center couldn't really, we don't have access to the middle element. So we might go up, in the worst case, we're still traversing the entire list. So we can't really throw out half the elements unless we keep, then the next, thing could be, keep a third pointer to the center element. And, that would, if you want to do the work to keep them sort of maintained at every step, and if that saves you, if that you care about those factors, that's how you implement it. But that doesn't change the running time in terms of what we're talking about. So now let's look at insert. How do we insert in a singly unsorted linked list? How would you insert? Yes? Sounds good. You just, the way we talked about, you just change the head, make the new element the head, and do the necessary pointer manipulations, and that would be order 1 work, right? If you insert in an unsorted linked list, it should be order 1. We talked about this yesterday. The way I would do it, and there are other ways to do this, is I will make the new element the head of the list and make the pointers make it point to the previous node that was the head. And now, because it's unsorted, I don't have to worry about anything else. It's just a pile of things in no particular order. So I'll just choose to add at the beginning. What if it's sorted? O of n. Why does the sorted thing doesn't help us? Yes, because it's sorted, so it actually hurts us because we can't put the element wherever we want. We have to find out exactly where to put it. So we have to traverse the list. Is this where I belong? Is this where I belong? Am I in between sort of these two things? Am I in between these? So you have a sorted list, but you have to find your place in this sorted list. That means you're searching. And if you're searching, your worst case order n. Is that clear? So if you're inserting in a sorted linked list, there's some sort of order that you have to maintain. So you can't put your element wherever you want. So you actually have to traverse the linked list, which makes it order n. What about inserting in a doubly unsorted? O of 1. Excellent. It's the same thing. Make the new element the head of the list. Doesn't matter. It's just unsorted. And doubly, the pointers only helps us in constant factors here. We change a few more pointers than before. It doesn't really matter. And if you have a doubly linked list and it's sorted, same issue as before. It's sorted. You have to find the place where you need to insert. So that means you're sort of traversing the list and going through everything. So it's order n. How about delete? We talked about this, and there was some confusion yesterday because of what I said and because of me. But now let's talk about it again. Let's talk about how do we delete in a singly linked list, unsorted, What's the best way to delete? I mean, let's come up with one naive way to delete. Yes.
I have a question about this one.
Yeah.
Is X a node or an element?
Good question. So node would mean, when you're talking about the node, it means the item and the pointer, or are you talking about whether it's the address or?
Yeah, I mean the element and the pointer, because if it's just an element, then you have to
Search for it.
before you can delete
Yes.
it.
So for now, let's say it's the pointer. Here, I'm okay with it being a pointer because then the search will not dominate the cost. So if you have a better way to delete, then that be it. I'll give you the pointer. I'm saying this is the location, delete this element. So all you have to do is do pointer manipulations. But because it's a singly linked list, we cannot sort of just loop back to we can't go to the previous element and change the pointer like that. So one way could be, and this is order n, and you'll know why, is I could go through the list and traverse the list until I hit the element right before me. And then I change its next pointer to the next element to the one that's deleted, getting deleted. So one way, and this is the order n inefficient way, but in some cases, I mean, this is the answer Steve's expecting, so it's fine. So one way, suppose I'm deleting this, is I don't have a pointer to this element. So I start from the beginning. I traverse the list until I hit the previous element, and then I change its next pointer to point to the element after it. So this way I can delete this. And now I don't remember, but someone suggested a better way to delete this, which I'm okay with, which is actually, or a clever thing you could do is you don't want to search for the element before this current element that you're deleting. You don't want to search for it, so what you would do is you would take the node immediately following it, whatever element you have in it, say you have element y, you just copy it over to this node, and then change this node, and then make the next node point forward. So you're only changing one forward pointer, and you're doing one copy of a record. Is that clear? That could be confusing potentially. And that's an order one. That's a constant time way to delete in a list when I give you the address of the element you have to delete. You don't want to change back. You don't want to go to the previous element and change the pointer there because you don't have a back pointer. So you would have to start from the beginning and find the previous element. So in that case, a better way would be to just copy the element after it into its current place and change the next pointer to skip that element and go to the next element. So in this case, yes. Very good question. That's what happens if you're deleting the tail, or if you're deleting the tail, then you just delete it. I mean, you make the forward pointer of the element before it just null. So you're given oh, you're right, yeah. Then you do have to do order n. So actually that does not work. Yeah, that's true. Let me think if there is a way that you could fix that. Like if you're deleting the tail, you do need access to the previous, yes? Yeah, I'm only giving you the address of the element that you're deleting. How do you go back to the element just before that? You just make that node null. Can you do that? I mean, you have to. You still have to. It's still in the list, so you're taking up that slot, right? Yeah, I mean, yeah, okay. That's one way. Just make that slot empty, and then you sort of have empty gaps in your list that you don't want. That's one way. If you're okay with wasting space, you could take the tail and just put garbage in it or make it empty and be like, hey, mark a dead cell. It used to be a cell. It's not a cell anymore. But that's not nice. Yes? Yeah, if you're keeping the address of the tail, then yes. I mean, he's saying just keep the pointers as is, and then make the cell sort of empty, and then yeah, yeah. So if you're maintaining the address of the tail, yes.
Yeah, I saw a single linked list that has a dummy node at the end,
Mm-hmm.
and I think that would solve this problem.
Yes, that's what he suggested. He said, if you're deleting the tail, just make it a dummy node.
Okay, what's the problem with that?
Well, you're wasting space. Also, if you're maintaining the reference to the tail, so if you're maintaining the address of the tail like you maintain the address of the head.
I think it ever maintain the tail pointer for single linked list, it would help.
Well, that's true. Yeah, that's true. It could if it was sorted and you wanted max or something, you'd go directly. I mean, so a lot of these things are like, what are the operations you want to maintain and how poorly you're willing to be on one to do to the other. And I agree that the nicest, I mean, keeping the pointer to the tail in a singly linked list and sort of making it dummy and things like that are not super nice. But, so now we've actually established that it cannot be made order 1, unless somebody is confused about that. So in the word, if you're deleting the tail, you can't really do that trick where you go back one and sort of copy it over. Yes? Yes. So that's the thing. Like if you.
There are a lot of ways to do it, but you didn't specify how to implement it.
Yeah, I mean, that's what I'm saying. Like, the thing is, you could maintain some additional invariance. So this, you always maintain the pointer from the tail to the head, and you keep updated. So that's the sort of work that you do no matter what operation you're doing, you have to maintain it. And if you're willing to maintain sort of additional information, which I didn't say you could, but if you're willing to maintain additional information, then yes, there are better ways to do this. But is everybody clear that at least order n is the not any extraneous information? Just look for the back point element behind you, change the next pointer. You could do order n. I'm going to do order 1 / order n because we're going to talk about like min and max and what information you're willing to maintain, and that could change this. And this order 1 is slightly iffy. I'm iffy about that, but let's just say that. Put a star here that, if you were clever enough and did it right, you could improve it. What about singly sorted? If I'm deleting in a singly sorted list, I'm given the address of the element, so I don't have to look for it, Yeah, yeah. Exactly. So you're still, the bottleneck still is that you have to find the element behind you, change the next pointer if you're doing it that way. And if you're doing something special, well, that's sort of up to you to make sure the correctness of everything else. How about if we do doubly unsorted? What's nice about doubly linked lists when we're deleting? All this issue that we were talking about back pointers and not having access to the element behind you is solved because you have a back pointer. Just go back to the previous element, skip over the current element, and make it point to the next thing that's not after the one that's deleted. So the issue we're having with not having back pointers is completely solved in doubly linked lists, so we get order 1. All right, doubly sorted. This makes me, my head is getting all confused. Maybe I should have done column-wise. Keep changing data structures. It's different. It's confusing for everyone. So all right, let's stop doing what we're doing and go, just fill up the columns. Oh no, fill up the columns. So let's fill up singly unsorted. How would I do a successor query? And remember, a successor is the logical successor. So if I have a list and I give you an element, I say come up with its successor, I would have to, yes. 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 Thank you. So you would have to go through the entire list. Does everybody see why? Because you have your own element and you have a list and you have to find something that's sort of just, if you're a sorted list, you want to find something that's just behind, in the logical order is your successor, so after you. So you would have to compare it to every element, every node in the list. And then that's how you get order n. How about predecessor? Same thing. Go through the entire list, compare the element with every element until you find the logical predecessor. It's a singly list, it's unsorted. So you don't know where things are in this list. So you have to go through everything. What about minimum and maximum? Order n. Can we do something cleverer if we wanted to maintain minimum and maximum and keep updating it? Could we do better than that? How much?
Well, whenever you, assuming you start with an empty list, whenever you add an element to the list, check to see if it's the minimum or the maximum and keep a pointer pointing to that.
Okay, so one way could be that if you weren't willing to sort of, yes, you can always do order n, and let me write that here. And then if you were going to sort of keep the promise of maintaining the minimum maximum every time you insert and delete, you could, in principle, do it in order 1. But then that could change the insert and delete cost. And that's important to see, like what operation depends on what other operation. Suppose I did ask you to do minimum maximum in order 1, then your insert and delete operation would have some additional work they have to do. Every time you insert an element, you'd be like, oh, is this my new minimum? If that's true, you would have to update your minimum. Every time you delete, you'd be, oh, is this my new minimum? Or is this did I just delete my minimum or did I just delete my maximum? And in that case, your delete and insert could become order n. Yeah. Yeah, so you have to look for it, right? Insert, does it become order n or does it become can you still do order 1? Insert, you could still do order 1 because if you're inserting something, you can check in order 1 whether it's the new minimum and update and just put it in the front of the list. So insert will still be order 1. And delete, I think, will become order n, but it's probably order n anyway. So you have to just keep in mind that every time there's a lot of correlation between these operations. So if you want to do really well in some of them, you might have to sacrifice the running time of other operations. So there's some inherent trade-offs. All right, let's look at sorted. These are really good for successor and predecessors. Why? Because now it's at least for successor, not predecessor. Let's not go that far. If in a singly sorted list, your successor is the next node in the ordering that you have. So your logical successor is also your physical successor because you're maintaining the keys in sorted order. So that would just be order 1. What about predecessor in a singly sorted? O(n), because I don't have back pointers. Worst case, I go through the whole list looking for the predecessor. Which element is my predecessor? Just check everything. We get order n. What about minimum and maximum? Minimum definitely O(1). That would be the head of the list because you're keeping it sorted. And what about the maximum? O(1). Maintain a reference to the tail and then go directly? Okay. Awesome. All right, we've moved on to doubly unsorted. It's getting really tiring. Come on, fast. Let's do it fast. Finish this. I want to be done with this. Doubly unsorted, you're doing successor. Yes? Did I say? No, it's ON. Oh, because it's a singly linked list, so you don't. Yeah. You can't go back. That's a doubly linked list. Two.